We all have bones. We feel them under our skin. Sometimes they hurt, and sometimes they make a popping sound. But we rarely think of them as being alive. The truth is, bones are not just dead sticks hidden inside our bodies. They are active, dynamic structures that change every single day. They are harder than concrete relative to their mass, yet flexible enough to absorb shock. Without them, we couldn't stand, move, breathe, or even live. It's inside our bones that our blood is created, where we store vital minerals, and where the history of our lives is recorded. Every fracture, every trace of disease, every structural change in our skeleton. And here's the most fascinating part. Bones constantly rebuild themselves from the inside out, adapting to how we live, what we eat, and how we use our bodies. This journey will show you an entirely new level of awareness of your own skeleton, from biology to evolution to the secrets bones preserve for years. Bones might seem rigid, cold, and unchanging, but in reality, they are one of the most dynamic tissues in the entire body. They are hard, yet living. They grow, rebuild, repair, and respond to everything we do. When we walk, run, lift weights, or on the contrary, spend hours sitting, our bones react, strengthening or weakening accordingly. Inside them, a silent, constant process of material exchange takes place. Old bone is broken down while new bone is built in its place. This process is called remodeling. Bones are made primarily of minerals and proteins. Their structure combines a hard mineral component, mainly a form of calcium and phosphorus called hydroxyapatite, with collagen fibers that provide elasticity. Thanks to this combination, bones are both strong and resistant to fracture, but also flexible enough to withstand impact without breaking. If bones were only hard, they would shatter like porcelain. If they were only elastic, they would bend like rubber. Nature created the perfect compromise between strength and flexibility. Bones are also perfectly adapted to life under gravity. Living on Earth means constantly fighting against the weight of our own bodies, and our bones are the tools for that struggle. They support us, transfer forces, and cushion every step. This is precisely why astronauts' bones weaken and lose mineral density in space. Without the constant load of gravity, their bodies see no reason to maintain strong bones, and the skeleton begins to weaken. Without regular, intense exercise and a special diet, it would literally start to melt away. It's also worth knowing that bones are home to bone marrow, where our red and white blood cells and platelets are formed. This is one of their most extraordinary functions. Hidden within our construction is a true blood-producing factory, working day and night without a pause throughout our entire lives. At the same time, bones are the body's largest calcium reservoir. When calcium levels in the blood drop, bones release some of their stored supply to maintain biochemical balance. So bones are not passive pillars holding us upright. They are a living tissue that reacts to change, adapts to life's conditions, and performs key functions: mechanical, metabolic, protective, and hematopoietic, that is, blood forming. When we start to see bones as an active organ, we realize they aren't just a scaffold, but an intelligent structure without which life as we know it couldn't exist. A bone, though it seems uniform, has a distinct architectural division. This is most visible in long bones, like the femur in your thigh, the tibia in your shin, or the humerus in your upper arm. Their basic structure consists of a shaft, which is a long central cylinder, and the ends on both sides. The shaft is thin, elongated, and primarily responsible for strength. It acts like a beam that transfers weight and forces. The shaft is what allows us to stand, walk, jump, and maintain our posture without collapsing. The ends of the bone, however, are thicker and more rounded. They often form the joint surfaces that connect one bone to another. This is where joints are created, the places where movement becomes possible. The ends don't just handle simple load transfer like the shaft. They disperse forces, absorb impacts, and allow for smooth motion. Thanks to them, your knee doesn't grind like a rusty hinge, and your hip can rotate in multiple directions. Interestingly, the ends and the shaft grow differently. Between them lies the growth plate, a layer of cartilage in children and teenagers that gradually turns into bone as we reach maturity. This cartilage is where bone lengthening occurs, which is why fractures in this area can be more complicated in young people and require extra care. The shaft is made mostly of compact bone dens and strong, whereas the ends contain more spongy bone, which has many cavities where marrow is located. This isn't an accident. It's nature's way of optimizing for both strength and lightness. Our bones must be strong enough to support our body weight, but light enough for us to move efficiently. If bone were solid like steel, we would be as heavy as robots and much less mobile. Together, the shaft and the ends form a perfect duo. One is designed for load-bearing, the other for cushioning and movement. Combined, they give our bones remarkable functionality, allowing us not only to stand and walk, but also to run, jump, climb, dance, and perform incredibly precise movements. Although most people imagine bone as a uniform, hard structure on the inside, it resembles surprisingly complex architecture. It's dense on the outside, and more like a lattice within. The outer layer is compact bone, an extremely dense and durable tissue. It absorbs most of the force, impacts, and body weight we experience daily. It has a highly organized structure and is crossed by microscopic canals carrying blood vessels and nerves. Thanks to this, bone is not a dead stone, but a living tissue that senses stimuli, receives nutrients, and can regenerate itself. Compact bone gives bones their raw mechanical strength. Without it, every step would risk a fracture. Inside the compact bone is the spongy bone. It looks like a network of tiny struts and beams, forming an airy, lattice-like structure. This architecture acts like a lightweight, but incredibly strong internal framework. Thanks to it, a bone is not just a heavy, solid block, but an ideal combination of lightness and strength. The spongy layer is excellent at absorbing shock, dispersing forces, and protecting joints from overload. And within its many spaces lies the bone marrow. Bone marrow is one of the most underestimated, yet most important, elements of the human body. In our common imagination, marrow is just something hidden deep inside our bones, something we rarely think about. Yet it keeps us alive every single day. Marrow is a biologically active tissue, constantly working, responding to the body's needs, producing blood, participating in our immunity, storing energy, and regenerating cells. It is a factory, a power plant, and a laboratory, all in one. Marrow comes in two main types, red and yellow. Red marrow is where blood cells are produced, red blood cells that carry oxygen, white blood cells that fight infection, and platelets that help our blood clot. This is where hematopoiesis occurs, the continuous 24-hour-a-day production of blood. Every single second, millions of new red blood cells are created, replacing those that get old and are removed from circulation. Our body doesn't care if we're aware of this process. It just works automatically to maintain balance. In a sense, the marrow reads the body's situation and adjusts cell production to current needs. If more red blood cells are needed after blood loss or at high altitude, the marrow speeds up production. If we're fighting an infection, white cell production increases. If there's an injury, platelet production rises. This incredible adaptability is key to our survival. The second type is yellow marrow, which is rich in fats and energy-storing substances. It is not inactive, it's the body's reserve that can be used when needed. Moreover, yellow marrow can convert back into red marrow if the body enters a crisis, like severe anemia or an extreme demand for new blood cells. This extraordinary flexibility shows that bones are not a static system but a dynamic one, constantly responding to life. With age, the ratio of red to yellow marrow changes. Newborns have almost exclusively red marrow because they need intense cell production to grow and develop their immunity. In adults, red marrow remains mainly in the flat bones like the sternum, ribs, spine, pelvis, and skull, while the long bones are filled with yellow marrow. This explains why serious marrow diseases often begin in these areas, and why bone marrow for transplants is typically collected from the hip bone. Bone marrow is also one of the most important components of our immune system. It's where immune cells are formed, which later mature and perform their functions throughout the body. This is where stem cells reside, cells capable of transforming into many different cell types, essentially renewing the body from within. A bone marrow transplant, used to treat diseases like leukemia, is in reality a transplant of an immune system, capable of reconstructing a patient's entire blood supply. Bone marrow is also an energy reservoir, a metabolic reserve, a place where the body stores resources for critical moments. Viewed in this light, it's impossible to think of marrow as just empty space inside a bone. It is the core of our biological identity, a foundation our life is built upon, even if we never see it with our own eyes. It's also worth noting that the ratio between compact and spongy bone changes with age. Children's bones are more elastic, more spongy, which is why they don't break with sharp, clean fractures as often. Instead, they might bend, crack, or deform. In older adults, especially after menopause, spongy bone can lose density. Its internal structures grow thinner and the bone weakens. This is when osteoporosis can appear, making fractures possible even after minor trauma. This dual-layered design, a hard shield on the outside and a light, flexible, biologically active structure on the inside, is a brilliant invention of nature. Because of it, a bone is not just a support. It's a dynamic, functional organ, adapting to our lifestyle throughout our entire life. The periosteum is one of those structures we usually ignore because it is invisible, and yet it is responsible for bone health, growth, and self-repair. It's a thin but incredibly powerful membrane that wraps around the outside of every bone, except where there's cartilage in your joints. This isn't just a passive shell. It's a bustling hub of cells, blood vessels, and nerves that basically runs the show for the entire bone. Inside this bark, you'll find special cells called osteoblasts. These are the master builders of your skeleton. When you're a kid, the periosteum is working overtime, adding new layers of bone, which is how your bones get thicker and stronger as you grow. In adulthood, its main job shifts from growth to repair, but it's always active, always on standby. Now, let's talk about blood flow. Bones are surprisingly thirsty for nutrients and oxygen, and the periosteum is their main supply line. Its rich network of blood vessels delivers everything the bone needs to stay healthy, like calcium and phosphorus. It also acts as an exit route, carrying away substances your body needs elsewhere. Your bones are in a constant, dynamic exchange with your blood, and the periosteum is the gateway. Ever wonder why a deep bruise on your shin or a broken bone hurts so much? You can thank the periosteum for that. The bone tissue itself doesn't have many nerves, but the periosteum is packed with them. It's a super sensitive alarm system. The moment your bone is in danger, it sends an immediate pain signal to your brain, telling you something is wrong. And when something does go wrong, like a fracture, the periosteum is the first responder. It instantly kicks off the healing process, sending stem cells to the injury site and forming what is called a callus, a sort of natural bone glue that patches things up. This is why kids heal so much faster than adults. Their periosteum is thicker, more active, and works in hyperdrive. As we get older, it thins out, which is why healing takes a bit longer. But that's not all. The periosteum also has another incredible job. It's the anchor point for your muscles. When you work out, your muscles pull on tendons, and those tendons are anchored firmly into the periosteum, not directly into the hard bone. This pulling action sends a signal. Hey, we need a stronger structure here. In response, the bone-building cells get to work, making your bones denser and stronger. So your bones aren't just a scaffold. They're a living, responsive system. So now we know the periosteum is the bone's guardian, but what about the bone itself? On the outside, it looks like a solid, hard material. But if you could zoom in, you'd see it's actually an architectural masterpiece, more like a high-tech bridge than a simple piece of rock. Its internal design gives it both incredible strength and surprising flexibility. The secret lies in its microstructure, particularly the spongy bone inside. It's not actually spongy like a kitchen sponge. It's a complex network of tiny struts and beams called trabeculae. These are arranged in precise patterns that perfectly match the typical stresses your bone has to handle. Think of it like the intricate truss system of a railway bridge, where every beam is placed exactly where it's needed for maximum support. This is why physical activity literally shapes your bones. An athlete's bones will have stronger, denser trabeculae in the areas that take the most impact. But strength isn't everything. Bones also need to be resilient. That's where collagen comes in. Collagen is a protein that gives your bones elasticity and stops them from being brittle. Without it, your bones would be like glass, shattering at the slightest knock. The collagen fibers are arranged in spiral layers, allowing the bone to absorb and disperse force without breaking. It has this perfect combination of hard minerals and flexible collagen that makes bone such an amazing material. What's even more incredible is that this entire structure is never static. It's constantly being remodeled. Specialized cells called osteoclasts act like a demolition crew, clearing out old or damaged bone tissue. Then the osteoblasts, our builder cells, come in and lay down new, fresh bone. This process happens throughout your life. Your skeleton is always adapting to your lifestyle. If you lift weights, your bones get denser. If you're inactive for a long time, your body starts to break down bone mass because it doesn't want to maintain a structure it's not using. So your bones are an intelligent engineering system, constantly fine-tuning themselves to provide exactly the right amount of strength you need. So we've covered the outer layer and the inner structure. Let's zoom out and look at the big picture. What do bones actually do for us? You might think of them as just a frame to hang our muscles on, but they are so much more. They are an active, multifunctional system that's essential for life. First, the obvious one: structural support. Bones give us our shape, allow us to stand upright, and enable us to walk, run, and interact with the world. Without them, we'd just be a shapeless blob. But remember, this support isn't static. It's a living system that responds to the demands we place on it. Second, protection. Your bones are natural body armor for your most vital organs. The skull is a helmet for your brain. The ribcage is a shield for your heart and lungs. The spine protects the spinal cord, your body's main information highway. Bones are designed to absorb shocks and will even fracture to sacrifice themselves to protect what's inside. Third, a function that's less obvious: mineral storage. Your bones are a bank for essential minerals, primarily calcium and phosphorus. And it's not just a storage vault, it's an active bank. If your blood calcium levels drop, your body borrows it from your bones to ensure your muscles, nerves, and heart can function properly. Your bones are a reservoir and a regulator all in one. Fourth, and this one is truly astonishing: blood production. Deep inside your bones, in the red bone marrow, your body creates red blood cells, white blood cells, and platelets. Every single day, your bones produce millions of new cells that are vital for carrying oxygen, fighting infection, and healing wounds. It is a paradox. The hardest part of your body is responsible for creating the liquid of life. And finally, movement. Bones act as levers. Muscles attach to them and generate force, while joints act as pivot points. It's pure biomechanics. Your muscles contract, tendons pull, and bones move, allowing you to jump, grab, and walk. Even the strongest muscle would be useless without the bony lever to act upon. So, when you put it all together, bones are performing structural, protective, metabolic, immune, and motor functions all at the same time. They are a storage unit, a factory, a framework, armor, and a tool for movement. There is no other system in the body that combines mechanics and biology so perfectly. Bones are not just the hard parts of our body. They are one of evolution's greatest masterpieces, keeping us moving, alive, and in one piece. Have you ever wondered how our bones grow from a baby's soft, flexible skeleton into the strong, sturdy frame of an adult? It's a journey of incredible transformation. When we're born, much of our skeleton isn't bone at all, the cartilage. This is why toddlers are so bendy and can bounce back from falls that would seriously injure an adult. This soft cartilage gradually hardens through a process called ossification. Think of it like building a house. You start with a flexible blueprint and slowly replace it with solid materials. At the ends of our long bones, like those in our arms and legs, there are special areas called growth plates. These are the construction sites of our skeleton. Here, cells multiply rapidly, adding new layers of tissue, which makes our bones longer. This is what fuels those amazing growth spurts we see in kids and teenagers. Hormones play a huge role in this. Growth hormone and later, sex hormones during puberty kick this process into high gear. This is also when our bones pack on density, becoming strong and resilient. Our bodies deposit massive amounts of calcium and phosphorus, building the skeletal foundation that has to last a lifetime. That's why a diet rich in calcium, vitamin D, and protein is so crucial when we're young. Any deficiencies during this time can lead to weaker bones later in life. Eventually, as puberty winds down, these growth plates close. The cartilage is completely replaced by bone, and that's it, we've reached our final height. This usually happens a bit earlier for girls than for boys. But just because our bones stop growing longer doesn't mean they stop changing. In fact, they are constantly being remodeled, a process that continues throughout our entire lives. This brings us to one of the most remarkable features of our bones: their ability to heal. Bone isn't a dead, static material. It's a living, dynamic tissue that can repair itself. When a bone breaks, the body launches an immediate and sophisticated emergency response. Within hours, a blood clot, or hematoma, forms at the fracture site. This isn't just a simple clot. It acts as a biological scaffold, bringing in immune cells to clean up damaged tissue and delivering nutrients to the repair crew. This repair crew consists of two main types of cells: osteoclasts and osteoblasts. You can think of osteoclasts as the demolition team. They get to work breaking down and removing jagged, broken bone fragments, clearing the way for new construction. Then the osteoblasts, the builders, arrive on the scene. They start producing a new bone matrix made of collagen and minerals, gradually bridging the gap in the fracture. It's a perfectly coordinated dance of destruction and creation. This healing process isn't instantaneous. It can take weeks, months, or even longer, depending on the severity of the fracture, your age, and your overall health. The bone first forms a soft callus of fibrous and cartilaginous tissue, which then hardens into a bony callus. But the process doesn't stop there. The final stage is remodeling, where the bone is reshaped and refined to match its original form and function. The regenerated bone isn't just a patch. It becomes a fully integrated part of your skeleton, strong enough to handle all the forces it did before the injury. But bone regeneration isn't just for emergencies like fractures. This remodeling happens constantly, even in healthy bones. Your skeleton is completely renewed roughly every 10 years. Old bone is constantly being broken down by osteoclasts and replaced with new bone by osteoblasts. This is how our skeleton adapts to our lifestyle. If you're physically active, the mechanical stress on your bones signals the osteoblasts to build more bone, making your skeleton denser and stronger. It's a beautiful example of form following function. This entire process is like a symphony conducted by our body. Hormones, vitamins like D, minerals like calcium and phosphorus, and growth factors all work in harmony. Calcium provides the building blocks, collagen gives it flexibility, and blood vessels deliver the necessary oxygen and nutrients. This incredible coordination ensures our bones not only heal, but also stay strong and functional throughout our lives. So the next time you think of your skeleton, don't picture a rigid frame. See it for what it truly is: a living, self-healing organ, constantly adapting to keep you moving, stable, and healthy. Now, let's explore the incredible diversity within our skeleton. Human bones are not all the same. They come in a variety of shapes and sizes, each perfectly designed for a specific job. Let's start with long bones. These are what you probably picture when you think of a bone: the femur in your thigh, the humerus in your upper arm. Their job is all about movement and support. They act like levers, allowing us to walk, run, and lift. Their long shafts are made of dense, compact bone for strength, while the ends are filled with spongy bone, which is great at absorbing shock and distributing forces across our joints. Inside, the hollow medullary cavity is filled with bone marrow, the factory for our blood cells. Next up are the short bones. Think of the small, cube-shaped bones in your wrists and ankles. Their purpose isn't to create long levers, but to provide stability and allow for fine, complex movements. Imagine trying to type or walk on uneven ground without them. Their spongy bone interior acts like a cushion, absorbing impacts and protecting these high-use joints from wear and tear during our daily activities. Then we have flat bones like the sternum in your chest, the scapula or shoulder blade, and the bones of your skull. Their primary mission is protection. The skull shields our brain, the sternum protects our heart and lungs, and the scapulae provide a broad, stable anchor for the powerful muscles of our shoulders and back. Flat bones are a marvel of biological engineering. They have a sandwich-like structure with two thin layers of compact bone surrounding a spongy bone center. This design provides incredible strength without adding a lot of weight. Finally, we have the most complex category: irregular bones. These are the bones that don't fit neatly into any other group, like the vertebrae in our spine or the uniquely shaped bones in our face. Their complex shapes are directly related to their complex functions. Each vertebra, for example, has to protect the delicate spinal cord, support the weight of the torso, and allow for a wide range of motion like bending and twisting. The intricate bones of our face create cavities for our eyes and nose, help us articulate speech, and provide attachment points for all the muscles that allow us to show expression. Each of these four bone types, long, short, flat, and irregular, is a testament to evolution's genius. From the powerful femur that lets us run, to the tiny bones in our wrists that let us grip, to the flat plates of our skull that protect our most vital organ, our skeleton is a masterfully designed system. It's a dynamic living framework that provides structure, enables movement, and protects us from harm. It's not just a collection of bones, but an interconnected system of specialized parts working together in perfect harmony. So, from the dynamic growth in childhood to the constant repair and remodeling throughout our lives, and the specialized shapes that define our form and function, our bones are truly extraordinary. They are a living testament to biological transformation, constantly adapting to our needs from birth to old age. Every step we take, every object we lift, is made possible by this incredible internal architecture. Did you know that humans aren't the only creatures with bones? It might sound obvious, but when you really dive into the animal kingdom, you'll find some truly mind-blowing skeletal designs. Let's start with birds, the masters of the sky. Bird bones are a marvel of evolutionary engineering, perfectly adapted for flight. Unlike our solid, heavy bones, most bird bones are hollow. But don't mistake hollow for fragile. Inside, they're reinforced with a crisscrossing lattice-like structure, kind of like internal scaffolding. This design keeps them incredibly lightweight without sacrificing strength. Reducing body weight is absolutely critical for staying airborne, and this is how nature solved the problem. This internal architecture is so efficient it resembles a miniature network of beams, perfectly distributing the mechanical forces from takeoff, flight, and landing. Think about the stress a bird's body endures. The bones of the wings and the sternum, or breastbone, are especially interesting. A bird's sternum is huge and has a prominent ridge called a keel. This is where the powerful pectoral muscles, the engines of flight, attach to power those strong wing beats. The wing bones themselves are long and slender, but they stay light thanks to those hollow cavities and a surprisingly thin outer layer of compact bone. But it doesn't stop there. To add rigidity for precise movements and to absorb the shock of landing, many bones in a bird's wings and legs are actually fused together. It's like they have built-in braces. And here's something really cool. Bird bones are connected to their respiratory system. The hollow spaces are filled with air sacs, which are part of a system that helps ventilate the body. This supercharges their respiratory efficiency, allowing them to sustain high levels of activity, like flying for thousands of miles during migration or performing sharp, rapid maneuvers. You've probably also noticed how flexible a bird's neck is. Many of their skull and neck bones are designed for incredible rotation, sometimes almost 180 degrees. This allows them to groom, find food, and keep a sharp lookout for predators with amazing precision. When you compare bird bones to our mammalian bones, you can really see how evolution tailors designs for different challenges. Our bones are heavy and dense, built for durability and resisting impacts from walking, running, and jumping on the ground. Bird bones, on the other hand, are all about being lightweight, springy, and optimized to minimize mass while keeping just enough strength. It's this incredible skeletal system that allowed birds to conquer the skies, making their bones a symbol of nature's genius. Now let's dive into the water and look at fish. Their bones are a whole different story, adapted for life in a three-dimensional aquatic world. Fish have a light, flexible skeleton that combines strength with amazing agility, which is essential for making quick turns, dodging predators, and catching prey. Compared to land animals, most fish bones are thinner and less calcified. This reduces their overall body mass and helps with buoyancy, making it easier to float and move in the water. The fish skeleton is divided into two main parts: the axial skeleton, which includes the spine and skull, and the appendicular skeleton, which is made up of the fins. The spine is incredibly flexible. The joints between the vertebrae allow the fish to bend its body in that classic S-shaped, wave-like motion that propels it forward. The skull is also relatively light and has lots of openings for blood vessels and nerves. Plus, their jaw connections are often movable, which makes them very efficient feeders. The bones in the fins, the pectoral, pelvic, and caudal fins create a flexible framework that gives them precise control over their direction and stability. It's like they have tiny built-in rudders and stabilizers. Many fish also have reinforced bony elements called fin rays, which add strength without adding much weight. The entire skeletal system works in perfect harmony with the muscles and the swim bladder. The swim bladder is an internal gas-filled organ that helps the fish control its buoyancy, allowing it to maintain a certain depth without having to constantly swim. Of course, fish bones also offer protection. The skull shields the brain and sensory organs, and in many species, scales or even bony armor provide an extra layer of defense against injury and predators. But even with this protection, the skeleton remains light and flexible, which is crucial in water, where every movement faces resistance. It's all about speed and responsiveness. From the sky and the sea, let's travel back in time to the age of giants, the dinosaurs. Dinosaur bones are a fascinating window into a world of extreme sizes and lifestyles. Unlike the light, hollow bones of birds, many dinosaur bones were massive, thick-walled, and incredibly strong. They had to be to support enormous body weights that, in the case of giant sauropods, could reach tens of tons. The vertebrae, limb bones, and skulls of these giants were often reinforced with internal structures. Some even had air-filled cavities, similar to birds, which helped to minimize weight while maintaining strength. But the design of dinosaur bones really depended on their lifestyle. Herbivorous dinosaurs, like the long-necked Diplodocus or Brachiosaurus, had incredibly long, massive leg bones and spines. These had to support their huge torsos and long tails while allowing them to move on land. Their skulls, however, were often surprisingly light, with numerous openings to reduce the weight of the head. This made it easier to munch on plants, even with powerful jaw muscles. Predators like Tyrannosaurus rex had a different toolkit. They had massive hind limb bones for power and speed, while their forelimbs were much smaller. Their jaws were built for crushing bone and tearing flesh. Their spines were both flexible and strong, giving them the agility they needed for hunting. Interestingly, some dinosaurs did have pneumatic or air-filled bones, just like birds. This is one piece of evidence that birds are modern-day dinosaurs. These air-filled bones reduced body mass and may have helped with thermoregulation. For a giant sauropod, having an efficient way to transport oxygen and maintain a stable body temperature would have been a huge advantage. Dinosaur skeletons also featured some amazing accessories. Things like tail vertebrae fused into clubs, horned skulls, or spiny projections weren't just for show. They served mechanical and protective functions and could have been used for display, communication, or defense against predators. For scientists, dinosaur bones are an invaluable treasure trove of information. Their structure, the preserved traces of blood vessels, microscopic canals, and the attachment points for muscles allow researchers to reconstruct how these animals moved, grew, and lived. The fossilized bones tell stories about mineralization processes and the environments these animals inhabited, from dry plains to humid forests. In short, dinosaur bones showcase evolutionary ingenuity at its grandest scale. From massive, weight-bearing structures capable of supporting a living skyscraper to lightweight pneumatic elements that enhanced efficiency, every bone was perfectly suited to the animal's lifestyle. It was this incredible skeletal framework that allowed these prehistoric giants to dominate the Earth for hundreds of millions of years. Diet plays a crucial role in the development, maintenance, and regeneration of bones, and proper nutrition can significantly influence their strength, mineral density, and flexibility. Most people know that calcium is good for bones, but the story is much more complex. Think of calcium and phosphorus as the bricks of a building. They form a crystal structure called hydroxyapatite, which gives your bones their incredible hardness and resistance to pressure. But you can have all the bricks in the world, and they won't do you any good without mortar and skilled workers. That's where vitamins D and K come in. Vitamin D is like the construction manager, making sure calcium gets absorbed from your food and delivered to the building site, your bones. Vitamin K is the expert mason, helping to produce special proteins that give bones elasticity and strength, making them less likely to fracture. Without these vitamins, even a calcium-rich diet won't be enough to build a strong skeleton. But what about the framework of the building itself? That's where protein comes in. Protein forms collagen, a flexible matrix that acts as the scaffolding for mineralization. Collagen is what gives your bones the ability to absorb shock and withstand dynamic forces from running, jumping, or lifting weights. It is the difference between a structure that's just hard and one that is both strong and resilient. So diet rich in calcium, phosphorus, vitamins D and K, and protein is the complete package for building and maintaining healthy bones. Now let's talk about the single most powerful stimulus for bone growth: physical activity. When you do weight-bearing exercises like running, jumping, or strength training, you're sending a clear message to your body: I need stronger bones. This stress stimulates specialized cells called osteoblasts to get to work, building new bone tissue and increasing your bone density. It's a classic case of use it or lose it. A sedentary lifestyle does the opposite, signaling to your body that strong bones aren't a priority, leading to gradual weakening and a higher risk of injury. This is crucial at every stage of life. Children and teenagers who are physically active and have a good diet build a higher peak bone mass, which is like putting more money in their bone bank for later in life. Of course, other micronutrients are also part of this intricate team. Magnesium, zinc, vitamin C, and B12 all play vital supporting roles in bone metabolism and collagen production. On the flip side, some lifestyle choices can actively harm your bones. Diets high in salt or caffeine can cause your body to lose calcium, slowly chipping away at your bone density over time. It's all about balance, giving your body the good stuff it needs and avoiding things that sabotage its hard work. Hormones are another major player in this story, acting as the master regulators of bone health. During childhood and adolescence, growth hormone is the primary driver, stimulating the growth plates in our long bones and helping us reach our full height. Then, during puberty, sex hormones, estrogen and testosterone take the stage. Estrogen is particularly crucial for women. It helps accelerate bone mineralization, and more importantly, it acts as a brake on the cells that break down bone, called osteoclasts. In men, testosterone supports bone mass directly and also by converting into estrogen in certain tissues, offering similar protective effects. But what happens as we get older? Around age 30 to 35, the balance begins to shift. The process of bone building starts to slow down, while the process of bone breakdown continues at its steady pace. This leads to a gradual, natural loss of bone mass. For women, this process hits the fast-forward button after menopause. The sharp drop in estrogen levels removes that critical brake on bone resorption, leading to rapid bone loss and a significantly increased risk for osteoporosis. For men, the decline is more gradual. Testosterone levels decrease slowly with age, but because some of it continues to convert to estrogen, men generally retain bone mass for longer. This brings us to osteoporosis, a condition where bones become so brittle and fragile that even a minor fall or a simple cough can cause a fracture. The spine, hip, and wrist are especially vulnerable. It's often called a silent disease because you can't feel your bones getting weaker. Osteoporosis is the result of a lifetime of factors, including hormonal changes, nutritional deficiencies, lack of physical activity, and even genetics. Other hormones can also throw things out of whack. For example, an overactive thyroid can accelerate bone turnover, while excess cortisol, the stress hormone, can actively inhibit the formation of new bone. It's a delicate hormonal symphony, and when one instrument is out of tune, the whole orchestra suffers. Now let's zoom in on the bones themselves because they are truly engineering marvels. It's easy to think of them as just dry, inert scaffolding, but that couldn't be further from the truth. Pound for pound, your femur, the thigh bone, is actually stronger than concrete. This incredible strength-to-weight ratio allows us to perform amazing feats every day. And on the other end of the scale, the smallest bone in your body is the stapes in your middle ear. It weighs only a few milligrams but plays a gigantic role in your ability to hear. Perhaps the most amazing thing about your bones is that they are constantly renovating themselves. Every single day, on a microscopic level, old bits of bone are broken down by osteoclasts and replaced with fresh new tissue built by osteoblasts. Your entire skeleton is essentially renewed over about a decade. This constant remodeling is what keeps your bones strong and able to repair microdamage throughout your life. And there's more. Tucked inside many of your larger bones is the bone marrow, a true factory of life. This is where your body produces millions of new blood cells every single second, red cells to carry oxygen, white cells to fight infection, and platelets to help with clotting. So your bones are not just your body's foundation. They're also a critical part of your circulatory and immune systems. They are a perfect self-regulating system, combining strength, flexibility, and regenerative power. So the next time you go for a walk, lift something heavy, or enjoy a meal with yogurt and leafy greens, give a little thanks to your incredible bones. They are working tirelessly, 24/7, to keep you strong, healthy, and moving through life.